Hello class, welcome to exercise 3i, exponential equations. In this lesson, your examples and pre-learning will be example 22, solving exponential equations. And your pre-learning for this example will be questions 1, 2, 3 and 4 in the new book and questions 4, 5, 6 in the old book. And then we'll do example 23, which will be solving exponential equations with a variable on both sides. And your pre-learning will be question 6 in the new book and questions 8 in the old book. Okay, I'm hoping this is going to be a fairly quick video. So let's just jump straight into the introduction. So we know that if a number a is raised to the power of n and the same number a is raised to the power of m and a to the n equals a to the m, then this could only be true if m was equal to n. But what if two different numbers raised to some unknown powers are the same? Well, there's actually no easy answer to this, and that's because we want the numbers to be the same base. However, if b was equal to a raised to the power of p, then a to the n equals b to the m will become a to the n equals a to the p raised to the m, just by subbing in a to the p for the b, right? So therefore we've now got a to the n is equal to a to the p times n, just by using the third law of indices. And therefore we know that n has to equal pm. Anyhow, there really isn't a lot more theory to this lesson. It's really all about the doing. However, I still think you should pause that video and do the building understanding questions in the new book, which are questions 1, 2 and 3 in the old book, because this will be a really good warm-up for the rest of the lesson. Okay, I'll see you in that next section. If we're presented with a to the x equals a to the y, then we know that x must be equal to y. Because if the same number was raised to different powers, we'd have a different number, right? Unless of course that number a is equal to 1. So this is all assuming that a is not equal to 1. However, if we're presented with a to the x is equal to some different number b, you need to rewrite b as a to the n. And that way we know that x will equal n. Okay, that's assuming you know what this n is. But sometimes you're going to need to convert both base numbers to ensure that they're now expressed with the same base. So for example, if I had 4 to the x equals 32, well, 4 to the 2 is 16 and 4 to the 3 is 64. So I can't just raise 4 to some power to figure out 32. But you can see that 4 is actually equal to 2 to the 2 and 32 is equal to 2 to the 5. So now we could start again with 4 to the x equals 32 and sub in these powers of 2. So we'd now have 2 to the 2 raised to the x is equal to 2 to the 5. And now we have the same base. So we can now see that 2 to the 2x is equal to 2 to the 5 just by using law 3. And therefore 2x has to equal 5, which of course means that x must be equal to 5 on 2. So that's about as deep as it'll get in this exercise, but please keep an eye out for negative indices. Because when you're using this method, you want to express 1 over a to the m as a to the minus m. Alright, let's just get into example 22 now, where we're going to solve for x in the following exponential equations. Okay, in part A, we've got 2 to the x equals 16. And that means 2 to the x is equal to 2 to the 4, because we know 16 is 2 to the 4, and we should rewrite 16 as 2 to the power of n, whatever that is. Okay, so we've got 2 to the x equals 2 to the 4, so therefore x must equal 4. Alright, nice and simple. Part B is 3 to the x equals 1 over 9. Okay, once again we've got a simple power of 3 here, but we do have a negative indice, okay? So you need to think about that as we go along. Alright, I'm going to rewrite 1 on 9 as 1 on 3 squared, so we get 3x equals 1 on 3 squared. And as I said above, we want to re-express that as 3 to the x equals 3 to the minus 2. And the reason why is because this is not the same base. I know it might look like it because you see a 3 there. but that's only true when it's rewritten with a negative index and 3 is at the base. Okay, so and from here you can see that that must mean that x is equal to -2. Alright, part C, we have 25 to the x is equal to 125. Now here we can see two numbers that are not the same base, but 25 is equal to 5 squared and 125 is equal to 5 cubed. So we could rewrite that as 5 squared raised to the x equals 5 to the 3, just subbing in the powers of 5 that relate to 25 and 125, right? So therefore we can say we've got 5 to the 2x equals 5 to the 3, and this could only be true if 2x was equal to 3, and of course that means that x is equal to 3 on 2. So this means that 25 raised to the power of 3 on 2 is equal to 125. However, you always write your answer this way, okay? Because all we're really concerned about is solving for x. Alright, so right now you should pause that video and get on to questions 1, 2, 3 and 4 in the new book, and questions 4, 5 and 6 if you have the old book. I think most of you will find that pretty straightforward. Alright, I'll see you in the next section. Alright, in this section, we're going to have a number a raised to a power x and a different number b raised to a different power. However, just like we did in the last section, we need to find a third number c where a equals c to the m and b equals c to the n. So that way a to the x equals b to the y becomes c to the m raised to the x equals c to the n raised to the y, just by re-expressing a as c to the m and b as c to the n. So now we have both numbers expressed as the same base raised to some power. So all we have to do is use the third index law, so c to the mx equals c to the ny. And then it's just simply a matter of solving for x. Now I'm not going to bother doing that with the algebra. Let's just jump straight into example 23, where you can see that it worked with a couple of numbers. Alright, so in example 23, we need to solve for x when we have the equation 3 to the 2x minus 1 equals 27 to the x. So I know that 27 is equal to 3 to the 3. So then we can use this in our new equation and rewrite it as 3 to the 2x minus 1 equals 3 to the 3 raised to the power of x, just by subbing in 3 to the 3 for 27. And using the third law, that becomes 3 to the 2x minus 1 equals 3 to the 3x. So as we've seen all through this lesson, that means that 2x minus 1 has to equal 3x. And subtracting 2x from both sides, minus 1 is equal to x, which is the same as saying x is equal to minus 1. Alright, and that's our answer. How about we actually check that? So if x is equal to minus 1, that means our left hand side there will be 3 to the 2 times minus 1, minus 1. And 2 times minus 1 is minus 2, minus 1 is minus 3. So we've now got 3 to the minus 3, which equals 1 on 3 to the 3, and that equals 1 on 27. Once again, with x equal to minus 1, our right hand side will have to be 27 to the minus 1, which is 1 on 27, which is the same as the left hand side, which is exactly what we want. Alright, so you can count that as a pro tip. Winners always check if they're not sure. Okay, pause that video now and do question 6 in the new book and question 8 in the old book. So this is a very quick lesson. When you finish that, we'll come back and summarize it. Okay, as we saw in the last section, don't forget to check your answers if you need to. And throughout this lesson and the last one, the algebra notes might have looked pretty serious, but in the end, they're still just numbers and equations that make perfect mathematical sense. Also, it would be great if you pushed yourself to the end of this exercise, so you know how tough exponential equations can get. That way, you will fully appreciate how convenient the method we're going to teach in the second half of this unit is. Alright, so a successful student will know the form of an exponential equation, be able to rewrite an expression using its lowest base, and be able to solve simple exponential equations using a common base. Alright, well done everybody. Work hard. As I said, try and get to the end of this exercise. We'll see you in the next class, whether that's in a video or in the classroom itself. Bye.